Hello and welcome to another Matlab tutorial. In this tutorial I'll teach you how to solve differential equations in Matlab numerically. In this example I'll use the ODE45 integrator. However, you could use, for example, other integrators like ODE13, but their purpose is the same, which is to integrate the derivatives of the differential equation. So to use these integrators, I'll first need to write the differential equation as y prime equals to some f of t, which could be time, and y. So the derivatives will be on the left hand side, and on the right hand side there will be the function that evaluates the derivative. So let's start by using a simple example, and let's solve the differential equation, which is y prime equals minus y squared. So to do that, I'll first need to define the function that evaluates the derivative. So function, and I'll call it dy, which is y prime, equals y prime. And here, as the first input, I'll need to input time, and as the second input, the value for y. So dy will simply be equal to minus y squared, as I said before. And up here I'll make the code to solve the differential equation using ODE45, and as the first argument I'll have to input this function handle, so at y prime. As my second argument, I'll have to input the time span in a time vector, and I'll want to solve the equation from 0 to 5, and as my last input I'll need to define the initial condition for y, so y0 will be equal to 1. And here, as the outputs, it will output me first the time vector and then the corresponding values for y. After this I'll just add a plot so we can see the results. Okay, I'll hit save and let's run the script. And as you can see, this is the result it gives me. The result of that differential equation solved from 0 to 5. Now to show you that you can also use derivative functions that depend on time, I'll simply add a new parameter here. And let's say instead of being just minus y squared, it will be minus y squared times the sine of 2t plus 1, like this. So I'll hit save and I'll run it again, and as you can see we now have these different parts here. So now it is using this function as the y prime function. You can also use this method to solve systems of differential equations. So y could instead be a vector. I'll demonstrate that now by solving a system of equations that has two differential equations and two state variables, so it will be a two-component vector. And to do that, I'll first need to define the function that evaluates y prime again. So function, and here, function, forgot to see. And here I'll put dy again, will be equal to y prime of t and y. Okay, now I'll define the vector dy, so the derivative of the vector y in respect to time will be equal, just as in the previous case, so let's use minus y1 squared times the sine of 2 times t plus 1, like this. And on the second component I'll use y1 minus 5 y2. This function will take as input the current time step t, which will be used here, and the current value for y, and we'll calculate its derivative. And once again I'll use the exact same input, so ty will be equal to ODE45 of at y prime. And let's solve it this time for 0 to 10 seconds. Now I'll need two initial conditions because I have two state variables, so one for y1 and the other for y2. And let's say y1 will start in the value 1 and y2 in the value 2. And here I'll put a plot again so you can see the results. And I'll save the function and let's run it. And as you can see, this is the result it gives me. So the orange curve is y2 and the blue curve is y1. So now I'd like to give you a physical example of an application of what I've just taught you. And to do that, I'll simulate a mass spring damper system. So let's look first at the function that evaluates dy dt. And first of all, I'll tell you that the y vector will be a two-component vector again, in which the first component will be the position of the mass, and the second component will be the velocity of the mass. So for the mass, I've used 10, it could be, for example, kilograms. For the damping, I've used the value 4, and for the spring, I've used the value 20. And here I'll define my vector dy dt, and the vector dy dt will have y2 in the first component because, well, the vector y, remember, is the position and acceleration. So the derivative of the position will be the velocity, so it will be y2, which is the velocity of the system. And in the second component, it will be simply the acceleration, which is calculated using this formula. So minus k times I1, which is the position, minus c times y2, which is the velocity, over the mass. And here I've used the exact same inputs. As you can see, I'll simulate the system from 0 to 10 seconds. And I'll start in the position 1 with velocity 2. And after this, I've just added a plot so you can see the system evolution. So I'll run this script. And as you can see, this has the typical oscillatory behavior. Let's look, for example, at the line for x1. So it started as 1, and as you can see, the derivative is positive, and indeed the velocity is equal to 2. And then it oscillates and dampens out due to the damping coefficient. So this is everything I wanted to talk about solving differential equations in Matlab. Thank you very much for watching this video, and if you like this video and if it helped you, please consider subscribing and liking this video, and hopefully I'll see you in another tutorial.